Hello Calc 3, welcome back to another video. In this video we'll be covering section 15.5 on triple integrals in rectangular coordinates. So in this video we define the notion of a triple integral, which is just an even broader generalization of the integral, typically for problems that involve higher dimensions. So functions in 3 variables or volumes of regions in 3 space. Okay, so let's build up the notion of the triple integral just like we've done for the double integral in previous sections. So we build the triple integral using the same method that we used for the double integral. So we can let f of x, y, z be some function in 3 variables, again with rectangular coordinates for us this time. And we can let r be some 3-dimensional region in space. So in the diagram that I've pulled from the book, I guess I used the letter R to denote the region in space. The book used the letter D, but it's the giant green shell that's in space there. And we can partition this region in space into boxes, like the one that we have in red. So remember that for double integrals, we partitioned the region in the plane into a bunch of smaller rectangles, but here we can use some rectangular boxes to make them 3-dimensional. We can then number all of the boxes from 1 to n, and the volume of each of the boxes is going to be exactly what you would expect. So the volume is going to be the change in x for that particular box times the change in y for that particular box times the change in z for that particular box. So we define the volume to be what we would expect it to be for each of these smaller boxes, and then we can choose a point x sub k, y sub k, z sub k for each of the boxes in the partition of the region in space here, and we can form the following sum, which is just a generalization of the Riemann sum that we had before. So we have S sub n is equal to the sum from k equals 1 to n of the function evaluated at each of the points x sub k, y sub k, z sub k times the volume of the kth box. So we take this sum here, and then the triple integral of f of x, y, z over the region R is defined to be, as you might expect, the limit of these sums as the norm of the partition goes to 0. So it's defined to be the limit as the norm of the partition of p goes to 0 of the sum from k equals 1 to n of f of x sub k, y sub k, z sub k times the volume of the kth box in the partition. And notice here that we could also write this triple integral like this over here, where we have dx, dy, dz replacing dv over here. Okay, so again, the definition is probably what you would expect it to be for the triple integral, and the way that we calculate triple integrals is going to be similar to the way that we calculate double integrals. We just have an extra variable to account for. Okay, so triple integrals most of the time are going to represent a volume of a region in space. So remember that for double integrals, we could use the double integral to give us the area of some region in the plane. Well, the triple integral does something similar. It gives us the volume of a 3-dimensional region. So if we let f of x, y, z equal 1, then the sums from above, those Riemann sums, S sub n is equal to the sum from k equals 1 to n of just the volume this time, because f of x sub k, y sub k, z sub k is always going to equal 1. And of course, as the norm of the partition goes to 0, our sum here is going to get closer and closer to the actual volume of the region. And this is how we define the volume of that region. So the volume of the closed bounded region R in space is given by v equals the triple integral of dv over the region R. So again, this is very similar to how we defined area using the double integral for functions of 2 variables. All right, so now we want to move down to discussing how we can actually calculate triple integrals. And remember from our discussion of double integrals that there was a way to represent a double integral as an iterated integral, and we called the theorem giving us that fact Fubini's theorem. And we can do a similar thing for triple integrals as well. So we can write a triple integral as 3 iterated integrals. And to say this a little more explicitly, to evaluate the triple integral of our function f of x, y, z over the region R in space, we perform 3 integrations that with respect to the variable z, the variable y, and the variable x respectively. And note that we can integrate in other orders as well. So in the example that I'm about to give, or maybe I should say the discussion that I'm about to have, we're going to be integrating with respect to z first, and then y second, and x last, but you could switch that order any way you want to, and the integral is going to end up being the same. I should also say that most of the time when the book talks about a 3-dimensional object in space, it calls that region D, and it calls a region in the plane R. So that's why you have the 3-dimensional object in space here labeled as D inside of the diagram. But the first step, whenever we have a problem like this, is to sketch the region that we're talking about in 3 space. And so we have a sketch of the region here. We have our 3-dimensional object D, and then notice that you also have a sketch of the projection of that object D down onto the XY plane, and that region is going to be called R. So we have 2 regions of interest here. We have our 3-dimensional region D, and we also have the 2-dimensional region R that represents the projection of D down onto the XY plane. Okay, so after we sketch the region, we have an idea of what we're dealing with, what this thing looks like. Because we're integrating with respect to z first, we first want to find the z limits of integration. So to do so, you can pick some arbitrary point xy down in the region R, so down here, and you can draw a line from that point xy parallel to the z-axis that goes up through the 3-dimensional region D. And our goal here is to find a function in the variables x and y that describes where that line is entering our region, and a function that describes when that line is leaving the region for all of the different lines that we can draw inside of the region R. And you can also think about these as surfaces in the space, because notice that we have, they're given as the function z equals f sub 1 of xy, which is going to represent a surface in space. And so after we have the functions in 2 variables that give us the upper and lower limits for z, we can move on to finding the y limits of integration. And again, this is because I had specified that we are taking the integral with respect to z first, and then with respect to y, and lastly with respect to x. So that's why we're moving on to the y limits of integration second. And to do this, we're going to focus specifically on the region R that's in the plane. And we're going to draw a line that is parallel to the y-axis that goes through the region in the plane. And the goal here is to find a function in x that expresses when that line is entering the region R, and a function in x that describes when that line is leaving the region R. So here we have y equals g sub 1 of x and y equals g sub 2 of x. So after we find the z limits of integration, we really only focus on the projection of D in the plane. And it kind of reduces to a problem that we would see with double integrals. So finding the limits of integration for y shouldn't be any more difficult than it was for double integrals. Finding the limits of integration for z might be more difficult because you have to think about a 3-dimensional figure this time, and sometimes those surfaces aren't obvious. The surface is expressing when the line is entering and exiting. But after we find our limits of integration for y, which again should be functions in x, then we can find the limits of integration for x. And this should be the easiest part of the process here, because once you get down to your last integral, you should just have limits of integration that are constants. So in the diagram above, you can see that we have a is the lower limit of integration for x, and b is the upper limit of integration. So at the end of the day, the integral of f of x, y, z, or the triple integral of f of x, y, z over the region D is equal to the following iterated integral. So we have the integral from a to b of the integral from g sub 1 of x to g sub 2 of x, of the integral from f sub 1 of xy to f sub 2 of xy, of f of xyz, dz, dy, dx. So notice here that the order in which we list dz, dy, and dx matches our order of integration here. Okay, so let's move on to the first example then. I do apologize that the example the book chose to give first is somewhat tedious, probably not the best example to choose if you're just introducing a topic, but the book chose to use this example, so I will go through it here. All right, so our task is to find the volume of a region D that's enclosed by a couple of surfaces in space. The first surface is z equals x squared plus 3y squared, and the second surface is z equals 8 minus x squared minus y squared. Okay, so note that the volume of this region D is going to be given by the triple integral of dz, dy, dx over the region D, as we discussed before. And again, the first step that we're going to use is to sketch the region, because we need to know what we're talking about before we can find the limits of integration here. And one important piece of information to sketch our region might be where the surfaces intersect. So we take our two surfaces, x squared plus 3y squared, and we set it equal to 8 minus x squared minus y squared. And then we simplify. We get things onto the right side, and ultimately we end up with x squared plus 2y squared is equal to 4. And this is an equation for an elliptic cylinder, because x squared plus 2y squared is equal to 4. If you forget about the variable z, that's going to be an ellipse in the plane, which you can actually see down in the diagram here in blue. But if you allow the variable z to roam, then we're going to get a cylinder where each cross section looks like that ellipse, x squared plus 2y squared is equal to 4. Okay, so, and as I already said, if we project this cylinder onto the xy plane, then we end up with the ellipse x squared plus 2y squared is equal to 4, which again is that region in blue down in the diagram. And so now that we have this, the curve of intersection, which hopefully allows us to better understand what the space looks like, we're going to find the limits of integration. So I'm sure that many of you right now are thinking, how on earth are you supposed to understand what this three-dimensional region looks like in space? This is a good question. So I know that 8 minus x squared minus y squared is a paraboloid, so that's not too hard to draw. And then we have z equals x squared plus 3y squared. That's going to look something like a maybe elliptic parabola, something like that. That's being rotated around the z-axis. So you kind of have a sense of what these things are going to look like, but maybe sketching them exactly is somewhat difficult. To which I would say, okay, so for the first example, our goal is to find the volume of some three-dimensional region D that's enclosed by two surfaces in space. So we have the surface z equals x squared plus 3y squared, and the surface z equals 8 minus x squared minus y squared. And we know from above that the volume of this region D is going to be given by the triple integral of dz, dy, dx over the region D in space. And our first step, as we just listed, is going to be to sketch this region in space. So one important piece of information for sketching the region might be to find where the surfaces intersect. And to do that, we can take our surface x squared plus 3y squared and set it equal to 8 minus x squared minus y squared. And doing a little bit of algebra with that equation there, we end up with x squared plus 2y squared is equal to 4. And if you set the variable z equal to 0, this equation x squared plus 2y squared equals 4 ends up being an ellipse in the xy plane. So down in the diagram that I have here, that would be that blue region that's drawn in the xy plane. But if you let z roam free, so it doesn't have to necessarily equal 0, then this ends up being an elliptic cylinder, which is just a cylinder where if you take any cross section that's perpendicular to the z-axis, you get the ellipse x squared plus 2y squared is equal to 4. So you can think about this plane that's drawn down in the region just being extended vertically, like these blue lines here. It's being extended vertically, specifically upwards. So after we know this piece of information, then we want to find the limits of integration. So you might be saying, well, we found the curve of intersection, but how do I know that the rest of this space looks like what's drawn here in green? Well, I would probably suggest to use some kind of software that you can find online to just plug in both of these surfaces, z equals x squared plus 3y squared and z equals 8 minus x squared minus y squared. And then try and get an idea of what that surface looks like just from viewing it online. Another way to do it is to say, well, I know that z equals 8 minus x squared minus y squared is going to look like a paraboloid, which with a height of 8. So this point up here is going to be 8, or 0, 0, 8, I should say. This will be 0, 0, 8. And it's going to be a paraboloid. So you can kind of think of it as a parabola that's being rotated around the z-axis that's going down towards the plane. And then you know that z equals x squared plus 3y squared is going to have cross sections perpendicular to the z-axis that look like ellipses. And these ellipses are getting bigger and bigger as we go up, which is going to give you that bottom green shape that you have right here. And if you think about it in that way, and maybe you draw both of those surfaces, it should at least give you the idea that you have this surface z equals 8 minus x squared minus y squared acting as somewhat of a cap for the surface z equals x squared plus 3y squared. And if you can just give a sketch that's good enough for that, and you understand the region in the plane, this x squared plus 2y squared is equal to 4, that's probably enough information about the region D to be able to find the limits of integration. Things don't have to be perfect or pretty or exact like they have it in the picture here, because, and you know, you can do that because you're using online software. But if you're not using online software, you really just need a good enough idea to find the limits of integration. And as long as you can do that, I don't care how pretty it is. Okay, so now we want to find the limits of integration for z because we're integrating with respect to z first. So we can pick any point inside of this blue region R in the xy plane, and then we can draw a line that's going up parallel to the z-axis. And notice that at all of the points inside of our region R, we enter D along the surface z equals x squared plus 3y squared. So that's the lower surface. And we exit D along the surface z equals 8 minus x squared minus y squared. So that'll give us our lower bound and our upper bound for z. For y, things I think are actually a little bit more interesting here. So again, when we're talking about the limits of integration for y, we're looking only at that projected region in the xy plane. So that region R. And again, we can pick a line and go up through the region parallel to the y-axis, and we notice that the line is always going to enter the region along minus the square root of 4 minus x squared divided by 2. So to find that, you just took the equation for the ellipse and solved for y. And so the lower half of the ellipse, the half on this side, is going to be represented by negative the square root of 4 minus x squared divided by 2. And the line is always going to leave on the other side of the ellipse, which will be represented as y equals the square root of 4 minus x squared divided by 2. So in this case, we have positive. In this case, we have negative. And then finally, we have to worry about our limits of integration for x. So this is the easiest out of the three. We can just look at our region R in the plane and notice that we go to negative 2 on the negative side, and we go to positive 2 on the positive side. So x is going to go from negative 2 to 2. And so now we can set up our iterated integral here for the volume. So we have the triple integral of dz, dy, dx. over the region D is equal to the iterated integral, where we have the integral from -2 to 2 of the integral from negative the square root of 4 minus x squared divided by 2 to the square root of 4 minus x squared divided by 2 of the integral from x squared plus 3y squared to 8 minus x squared minus y squared dz dy dx. So that is certainly a mouthful, which is why I think that it probably wasn't a great decision for the book to start with this example here. Maybe something a little bit easier would be nicer. But anyways, we'll work through it. Okay, so we take the inner integral here with respect to z. So we're just taking dz, or the integral of dz with respect to z, and that'll give us just z. And again, we're evaluating from x squared plus 3y squared to 8 minus x squared minus y squared. So then we can plug in 8 minus x squared minus y squared and subtract x squared plus 3y squared. And we get this 8 minus x squared minus y squared minus x squared minus 3y squared dy dx. We can combine some like terms to make it look a little bit more pretty before we integrate a second time. And then we can move on to integrating with respect to y. So notice that I've, instead of writing the square roots over and over again, I just decided to abbreviate those functions in x with g sub 2 of x and g sub 1 of x, just to make life a little bit easier. Okay, so we integrate 8 minus 2x squared minus 4y squared, and we get 8y minus 2x squared y minus 4/3 y cubed. And again, we're evaluating from negative the square root of 4 minus x squared divided by 2 to positive the square root of 4 minus x squared divided by 2. So we can take both of those expressions and plug them in for y in the same way that we usually would for integrals. I tried to simplify a little bit before I plugged those expressions in because the resulting expression is really gross. And some of the calculation is legitimately just too tedious for me to even want to talk through on YouTube. If you really want to see it, the book might give it in a tiny bit more detail. But the point of the example really shouldn't be about the calculation anyways. It should mostly be about setting up the limits of integration and then kind of showing how the integrals or the triple integral works when you write it as an iterated integral. So there's some calculation in between here after you substitute in with this square root of 4 minus x squared nonsense. And ultimately, it simplifies to this integral here. So we have 4 times the square root of 2 divided by 3 times the integral from -2 to 2 of 4 minus x squared to the 3/2 dx. And again, I'm not going to show the method for how to calculate this integral, but to calculate it, you would use trig substitution, where you let x equals 2 times the sine of u. And so if you need to review that method of integration, then you can again open up your book to, I think that's chapter 8 in the book. So you could review it there if you wanted to. I'm not sure if you're going to have to use this kind of integration method on the homework, but if something like this shows up, then you could always just go back and review it from chapter 8. Okay, so let's move on to a second example then. For the second example, we're setting up limits of integration for evaluating the triple integral of some function f of x, y, z, which isn't given to us yet, over the region D, where D is the tetrahedron with the following vertices. So it's the tetrahedron that's formed by the points 0, 0, 0, just the origin, 1, 1, 0, 0, 1, 0, and 0, 1, 1. And we're going to use the order of integration dy, dz, dx. So we integrate with respect to y first, then z, then x. All right, so again, the first thing we always do for these types of problems is to sketch the region that we're talking about. So we're going to sketch the tetrahedron in three-dimensional space here. Again, the book does a better job at sketching this kind of stuff than I do because they have computers to do it. So I just stole a picture from the book here. But if you wanted to sketch it by hand, it actually wouldn't be too bad for this region here. So you would end up just plotting the points that are given to you in space, and then you're going to draw planes through those different points in such a way that you can form the tetrahedron that shows up here. Again, it's going to be somewhat messy to draw this kind of picture, but it can be done at least well enough to get an idea of what the limits of integration are going to be. But again, I chose the book's picture because it's just going to look much nicer than the one that I would draw. Okay, so we are integrating with respect to y first, and then z, and then x. So the first thing we want to do is find limits of integration for y. So if we draw a line that's parallel to the y-axis, this line is going to enter the tetrahedron along this green plane, this kind of green triangle on the left, and it's going to exit the tetrahedron through the rightmost plane, or I don't know what color that is, maybe like a lighter green plane that shows up on the right of the tetrahedron. So we want to find functions in x and z that express these planes here that are being drawn, because those planes are going to be the lower limit and the upper limit for y. And this takes us back to chapter 12, where we found where we discussed how to find equations for the plane that contains 3 different points. So the left plane, the plane in green here, consists of the points 0, 1, 1, 0, 0, 0, and 1, 1, 0. And to find the equation for the plane, we're going to want a vector that is normal to that plane, and then a point that's on the plane. So to find a vector normal to the plane, we take 2 vectors that are in the plane and then take their cross product. So using the points that are given above, we find that 0, 1, 1 is a vector in the plane, and 1, 1, 0 is a vector in the plane. So their cross product is going to be a vector normal to that plane. And we evaluate the cross product here, and we find the vector -1, 1, -1. And then we can just use the formula for the equation of the plane that we had from chapter 12. So the equation for that plane on the left, the plane that's green here, is going to be -x plus y minus z equals 0. And if we make that look a little bit nicer, we solve for y so that we get a function in x and z. We get y equals x plus z, which is exactly what shows up inside of the diagram here. So that's a good start. Okay, so that's the equation for the plane on the left. We also want an equation for the plane that's on the right that represents when those lines parallel to the y-axis are leaving our region. So the right plane consists of 3 points as well. We have 0, 1, 1, 0, 1, 0, and 1, 1, 0. And so we have these 2 vectors lie on the plane, the vector 0, 0, 1 and 1, 0, 0. And if we take the cross product, we just get the vector j. So the plane could be written as y minus 1 is equal to 0, which just goes to y equals 1. So an equation for the plane on the right-hand side of our tetrahedron is going to be y equals 1. So we can finally say that the limits for the variable y are going to be x plus z and 1, where x plus z is the lower limit and 1 is the upper limit. Okay, so now we want to find limits for z, since we have our limits for y, and z is the next variable of integration. So the projection of the tetrahedron onto the xz plane gives us a triangle, which is given in our diagram here. So it gives us this blue triangle, which the book calls R. And I gave another picture of it here. So we have, it's the triangle that consists of the line segment from 0, 0, 0 to 1, 0, 0 along the x-axis, and then the line segment from 0, 0, 0 to 0, 0, 1 along the z-axis, and then the line that's connecting those 2 points, or the hypotenuse of the triangle. And we want to find an equation for the line that represents the hypotenuse of this triangle, because if we take lines that are parallel to the z-axis that go up through our region, we know that those lines are going to enter the region along x equals 0, just along the x-axis, but they're always going to exit the region along that line that's connecting the point 0, 0, 1 and 1, 0, 0. And the hypotenuse ends up being the line z equals 1 minus x. And so the lower limit is z equals 0, and the upper limit is going to be z equals 1 minus x for our variable z. And then finally, the easiest limit of integration to find, we have that x is between 0 and 1. So you can just see that even from are drawing here in the xz plane. So x goes from 0 to 1. And so finally, the integral of f of xyz over the region D is given by the integral from 0 to 1 of the integral from 0 to 1 minus x of the integral from x plus z to 1 of f of xyz dy dz dx. So again, another mouthful, but that's how it's going to look. And now, if we want to find the volume of the tetrahedron, we can just let that function f of xyz equal 1, and then we can calculate this iterated integral here. So that'll give us the volume. So we take the inner integral first with respect to y, and we get y evaluated from x plus z to 1. So we plug in 1 and subtract x plus z to get this 1 minus x minus z. And now we integrate with respect to z, and we get z minus xz minus 1/2 z squared from 0 to 1 minus x. And again, we can plug in 1 minus x for z, and we get this expression, 1 minus x times 1 minus x minus 1/2 times 1 minus x squared. And there's a bunch of algebra that goes on here, just expanding and then combining like terms to make it look a little bit nicer. And we get down to the integral from 0 to 1 of 1/2 minus x plus 1/2 x squared dx. And we take the integral again, we get 1/2 x minus 1/2 x squared plus 1/6 x cubed evaluated from 0 to 1. And if we plug in 1, then we get a 1/2 minus 1/2 plus 1/6. And so ultimately, the volume of this tetrahedron is going to equal 1/6. All right, so finally we can move on to the last topic for this video, which is to extend the notion of the average value of a function to functions in 3 variables. So as you might expect, based on the definitions that we had from the previous videos, the average value of our function in 3 variables f over some 3-dimensional region D is equal to 1 divided by the volume of the region D times the triple integral of f over the region D. So for example, if our function f in 3 variables was equal to the square root of x squared plus y squared plus z squared, notice that this function here represents the distance from a point to the origin in 3-dimensional space. Then we would get the average distance from the points inside of some region D to the origin. So that's a pretty cool application of the average value given above. Okay, so let's move on to our only example for average value here. This is the last example for the video, so stick with me. So let's say we want to find the average value for the function f of xyz is equal to x times y times z throughout a cubical region D that's bounded by the coordinate planes and the planes x equals 2, y equals 2, and z equals 2. So fortunately, I can actually sketch this region by hand. So this is the only region in the video that I feel comfortable attempting to sketch so that you can understand what I'm talking about. But we have this cube here. This is x equals 2. This is y equals 2. And this up here is z equals 2. And we can integrate with respect to z first. So the nice thing about integrating over cubes in 3-dimensional space is that all of the limits of integration are going to be just constants, just as simple as possible. So the limits of integration for z are going to be 0 to 2. The limits of integration for y are again going to be 0 to 2. And the limits of integration for x is again going to be 0 to 2. So we know that the volume of a cube is equal to the side length cubed. So the volume of this cube here is just going to be 8. And so the average value, using the definition that we had above, is going to be 1 over 8, since 8 is the volume of the cube, multiplied by the triple integral of x, y, z over the region D. And we can write that again as the iterated integral from 0 to 2 of 0 to 2 of 0 to 2 of x, y, z, dz, dy, dx. And then we can take the integral of x, y, z with respect to z from 0 to 2, and we get 1/2 x times y times z squared evaluated from 0 to 2. We plug in the 2, and we get 1/2 times x times y times 4. And we can simplify a little bit and end up with 1/8 times the integral from 0 to 2 of the integral from 0 to 2 of 2 times x times y dy dx. And so now we move on to taking the integral with respect to y from 0 to 2. And we get 1/2 times 2x times y squared from 0 to 2. Again, the 2 and the 1/2 are going to cancel. And so we end up with just this x y squared from 0 to 2. We can plug in 2 and we get 4x. So we're left with 1/8 times the integral from 0 to 2 of 4x dx. And of course, the antiderivative of 4x is going to be 2x squared, and we're evaluating from 0 to 2. So we plug in 2 for x, and we get 1/8 times 8. And so the average value of the function x times y times z over the cube that was given as our region here is going to be equal to 1. Okay, so this is probably the easiest example that was in the section. I kind of wish that the book would have started off with examples that had regions like this cube that are a little bit easier to handle. But at least we got to somewhat of an easier example by the end of the chapter. So I do want to note before I get to the end of this video here that many of the calculations that are going to pop up inside of these triple integrals are going to be long and tedious. Lots of little minus signs that might get lost, things like that. Lots of square roots that can cause problems. So it's usually a good idea for these kind of problems to check your work with some kind of software that you can find online, or if you do have a graphing calculator that will do some of these integrals, checking with that might be nice too. Just remember that you shouldn't do this on exams because I don't want you using calculators or the internet on exams, but feel free to do that for quizzes. Again, the internet is a great resource for checking answers. So yes, that's all the information that I have for section 15.5. We will be skipping over section 15.6 and going right to section 15.7, and that video should be up by Monday.